we're going to look at CEDAR, which is a C++ framework which we've developed at our institute in the last 10 years or so. And this is a standalone application that you have to download. You can get there if you go to dynamicfieldtheory.org under Learning DFT, and you then go to software. We have two software frameworks. This you may have already seen. The Cosivina is a MATLAB-based framework, which we also use for kind of some different work. But now we're interested in CEDAR. Here's a little snapshot of what that looks like. So if you click on here, set up CEDAR, you land on the CEDAR webpage, which is cedar.ini.rub.de. And there you can go to download. And we have, for the main operating system, Windows, macOS, and different shades of Linux. These are, I think, Debian-based, so Ubuntu-like Linux versions. We have precompiled versions of CEDAR where you just have to download, the version for whatever operating system you're running, and you should be good to go. You don't have to compile anything. Or if you have some kind of strange version of Linux, or some old version of macOS or anything where that doesn't work, there is still the option of running that from so compiling CEDAR from source. It's an open source project. It's a bit involved, so I'm just crossing my fingers that it works for you. So just you can just download that. I did that already, and I have it here. You download a tarball, which you then extract, and there's a folder here, CEDAR, which a bunch of stuff that you don't have to look at. The only thing is the CEDAR app, or I think under Windows it's called cedar.bat file, which you just click, and then it should start an application that looks like this. And this is the graphical user interface of CEDAR. And this is where you basically do everything in this program. So it's a program that allows you to build architectures and change parameters and plot things, all while simulating the architecture. So there's a large canvas here where you can assemble elements, and the elements are up here. So there are a few here. There's more tabs where you can look into a lot of different stuff. We only going to need a few things. So the way you work with this is you take one of the elements, for instance, a neural field here, you drag it onto the canvas and you drop it there. This now created an instance of a neural field. So it's this little icon where the field is this box, and it has a little input thingy here on the left side where you can add input from other sources. And it has a little output box on the right side. I'll show you how you can then use them later. And you can instantiate more of these, just drag and drop elements from up here. You can select them and delete them, like clicking delete. If you select any element, you have a whole bunch of parameters here on the right side. So for instance, here you can change the name and say, for instance, test field. That'll also change a little bit. Sometimes here, some of these, some what is shown here. You can change the dimensionality. So make, for instance, a one-dimensional field. This size is how it's sampled, the time scale, and a lot of parameters that you also know from the other simulators. And to then simulate this whole thing, there's a play button up here, which you can just click, and then this is now simulating and approximating this differential equation that determines the neural field. You can kind of see that it's running from this switching to a different symbol, and all the field elements, for instance, have this little green thing here. This is now simulating that. Now, whenever it's doing anything, you can also look at what is going on by plotting different elements of an architecture. If you right-click on to this field, for instance, there's a section plots here where you can plot then the activation, the output, the kernel, and all these kinds of different things. There's sometimes also predefined plots like the field plot here. If you click on this, you'll find a plot like the ones that you're used to from the other simulator, where you have activation here and the output and the input here. You can also right click in here and you get a legend, which is a bit more helpful than just these lines. Right, and now since it's already simulating, you can now monitor what is going on. This is now a little boring because this is just a field without any input. If you want to add in some input, we do this through more elements. So there's an element up here called Gaussian Input or Gauss Input. If you drag this in here, it's a little box like that. And it only has an output on the right side. So it produces a Gaussian function. And you can now connect these two things. When you connect elements, you always have to make sure that they are of the same dimensionality and they're sampled the same way. So this is dimensionality, has dimensionality 1, has the size of 50, so there's 50 sampling points. And for the input, that has to be the same. By default, these two elements are created two-dimensionally. So we reduce the dimensionality here to 1, and the size is already correct. And then to connect, we can draw a line from the output of this thing to the input of here. And you can see that it's working first because the line is green. That's a good sign. And also because the input showed up here in this in the activation of the field. Right? And now if I make changes, for instance, to the input, if I click here, I can change the parameters of the input, for instance, change where that Gaussian is centered. And you see that that has an effect. Oh, I can also plot the Gaussian. Looks like this. You can see that that has an effect both on the Gaussian and also on the activation here. This is the actual input to the field, so the exact Gaussian here. I can also change the amplitude. You can see right now that the input isn't strong enough to go above threshold. Threshold here is at 0, like always. But if I make this stronger, at some point, I get a little peak. You also notice that the symbol here changed from no peak to peak. It's a little indicator that there's now a peak in the field. And there you go. Now you can very quickly assemble a simulator like the one that you used, this web-based simulator, with just this little field and a few inputs. You can kind of get the same functionality, but you built it all yourself, right? And this is one of the main advantages of CEDAR, that you can just build whatever you want to use. There's a whole lot more functions that I'm not going to get into right now, but what I want to do is go through the CEDAR tutorial that are also put on the web page and kind of show you how to solve parts of it. So we'll delete all of these things. So we have a blank slate again. So the thing I'm talking about is if you go to the summer school website. Oh, this doesn't work, this tab. So we go to the website here, we click on the event, we go to documents, and then down here you have the CEDAR tutorial and exercise. And if you click on this, that's a PDF file like the exercise that you worked on. And this has a step-by-step explanation basically of what I'm going to do now. So I'll do a few of these, and then there's an exercise in the end, which I'm not going to do, but you can explore that on your own. So what we're going to build are three-dimensional fields, and that also tackles a little bit of the question that somebody just had of how to get the right parameters. So the first thing that we want to build is a field that has multiple peaks and just goes through the detection instability. And then later we have a working memory field and a selective field. And we'll do all of this by hand, basically. So let's go back to CEDAR. So the first thing that we want to create is a field. and we did that already, but this time it's going to be a two-dimensional field. If we plot this, this is the field, sorry, right-click field plot. It looks like this. And what you see here is first the input to the field, and you can see that there's no input at the moment. The activation of the field. Here you can see that there's some noise in the field, but other than that, it's at threshold at resting level. So at between -5.1 and 5. That's just because of the noise, and there's no output in the field, right? And we want to use this field sort of as a representation of objects on a table, like a tabletop. So imagine that this space here, these two dimensions are a table looked at from the top, and peaks in this field are then objects on the table. And usually we would use, maybe a camera setup that is like that then feeds activation into the field. We usually do that in our lab like this, but since all of you have to do this at home, we can't provide that setup. And it's also much easier if you have simulated input. So we'll start with this for now. So we will build a simulated scene out of Gaussian inputs. And the way we want to do that is, let's say we want 3 different objects, then we use 3 Gaussian inputs here. We'll just drag these in. And close this for now. If we then plot one of them, we can now change the parameters of that Gaussian. So imagine this is now the tabletop, and this is one object, and we'll just move that around to one corner. And then we have a second object. We'll also move that somewhere else, so they're not in the same place. And then there's a third object. Plot this and move that into the maybe bottom left corner. Doesn't really matter where they are. It just shouldn't overlap. And then to create a single scene, we'll just take these 3 Gaussians and sum them up. So we connect these all to this sum step. This one. It just takes all the inputs and sums them. So if we plot this, you can see now these are the different inputs it has, and this is the sum. So all 3 objects here. And if I now change one of these object locations, you can see that the scene changes a little bit, right? And we'll use this as sort of a scene representation. You can maybe imagine that, we have a camera set up looking down on a table, and there's a few objects that we can move around by hand, and we'll just simulate that here. And now we can make the output of the sum input to the field, but we'll put in this static gain thing in the middle. So what that does is just multiply the strength of what comes in with a scalar value, and then puts that into the output. So that allows you to make basically the strength of the objects globally stronger or weaker. So we'll put that into the field. And now if we plot the field output, you'll see that there's this input here, and that has an effect on the activation. If you look at the plot here, it looks like there may be 3 peaks, because there's these 3 blobs of input here. But if you then look at this color bar, you see that the activation values are only between -5 and -4. So the way this plot works is it takes the lowest and the highest value and maps these anything in between to these colors. So when you look at this activation plot, make sure that that you read it right, because sometimes you may look at it and think, oh, there's 3 peaks, but there really aren't. If you look at the output of the field, there isn't anything in here. So if there were 3 peaks, you should see 3 little red things here. So the problem right now is that the input isn't strong enough, and we can change that with this static gain. If we ramp this up, I'm doing that now, you can see that the activation, the maximum activation in the field also goes up. And at some point, we ramp this up to 7, you now have peaks. The plot looks the same, but the maximum activation here is above threshold. And you also see that there is an output of this field. So it's now producing output which can have an impact on other fields. This is already the solution to the first task. So this is a multi-peak field, which just went through the detection instability. We can give this maybe a name so that we know later what it is. We'll call this multi-peak. Apparently I can't type. And this is, where is it? This is basically what you're doing here, right? There's also little questions in here that you can follow up on. What happens when you change objects, when you take them away, and so on. So you can do that on your own time. I can kind of show you that when you move something here, you also see the activation moving, right? But then try to think about, and this I think is important. Try to think about what should this field be doing. If I now take an object off the table, do I want it to keep the peak there, or do I want it to go away? Do I want the field to only have a single peak, even if there are multiple objects, or not? These kinds of decisions, and that has to do with what kind of function that field has in your architecture. Good. So the second field that we want to build is, if we go here, is a working memory field. And I'll not go through the text. You can read that later. But basically, we want a copy of this field, which we can just create if you pull down another field here, and we will just call this working memory. And then connect it to the same input. So it now gets the same sort of simulated scene input as the other field. Otherwise, it's not really connected to this field. So whatever this is doing doesn't have an effect on the working memory field, right? Because this isn't connected to anything. But now the behavior of this field should be different in the sense that if I take an object off the table, or if I remove it somehow, that the peak in this field should stay, right? So how do we take an object off the table? We can go here, we can move them around, but taking it off would mean it disappears. So what we can do is remove the strength, the amplitude of that particular object to 0, and we can see that it disappeared, right? This is not the behavior that we want. We can also see that in the other field, the multi-peak field, it also disappeared. So we want the working memory field to be self-sustained in the sense that when I do that, when I take an object out, the peak stays there, right? And this is sort of where this idea of tuning comes in. You now know what kind of function you want, and you have to now figure out what kind of parameters do I want to change and how do I change them. If you understand fields, you know that if I want a self-sustained regime or working memory regime, I need a lot of self-excitation, so to build up activation, so that when I take away the input, that field still stays there, right? So that means a lot of self-excitation in the kernel. In CEDAR, the kernel parameters are a bit convoluted. I'll try to explain that. So there are here, if you click on this field, you go here to the right side, you scroll down a little bit. At some point, you'll find a section called lateral kernels. And there's then a list of kernels. It says here lateral kernel 0, so that's the first one. And it says it's a Gaussian shaped. Usually what the kind of kernel shape that we want is a Mexican hat kind of shape, which I don't know if you can see this, looks like that, right? So we want some excitation in the center and then some inhibition on the side. And right now we only have the excitation in the center. That's from this thing. So it has an amplitude which is positive, which gives you the excitation, and that's it. So there is a second parameter here for global inhibition. This is negative, but that would mean it would give us a shape where you have excitation in the center, but then inhibition on the sides everywhere. This is for selection. This is not what we want. So we change the global inhibition to 0 for now. And then, oh, and I remember I took this object out. I'll put that back in. And then, so we want a lot of self-excitation, right? So we ramp up the amplitude here of the kernel. And you can already see that that is doing something because the activation here, the maximum activation, is going up, even though I'm not changing the input. So if I do this for a while, you'll see that those peaks are going to grow and grow. And well, now they merge, and at some point, everything is going to go above threshold. This is because there's a lot of self-excitation, but no inhibition to counteract that. Right? There's now a single huge peak which fills the entire field. And this is not what we want, right? We want individual peaks that are strong, but still separate. So we need some inhibition. And the way to add this here so that you have still multiple peaks is not by global inhibition, by mid-range inhibition. There is a section here where you can add new kernel modes. So you can, if you click here on Gaussian, because you want a Gaussian shaped kernel, then you click on the little plus button. This will give you a second kernel mode. And we can now make this one negative. So this is the excitatory part that we already had. And we can make this broader and negative. So if we, for instance, if we set this to minus, where's minus here, 12, and we make it broader, good rule of thumb is to make it twice as broad as this. Then you already see that now this blown up activation is gone because there's now some inhibition, and you kind of see this kernel shape as these little rings here. If you right click on working memory on the working memory plot and you plot the full lateral kernel, you now see that, make this a bit larger, oops. This is the shape of the Mexican hat, right, from top. So you have the excitatory kernel mode, which is this part here. And then you have the inhibitory thing, which comes in from this negative but broader thing. And the kernel is just made up of the sum of these two kernel modes. So if I make this even stronger, you'll see that there's more and more and more inhibition, right? And if I make this stronger, the center becomes stronger. We can now test again. If I take an object out, you can test whether that peak sticks around, and still it doesn't. So this is just the test that you do, right? You take objects out until, and then change parameters until you get the function that you want. So if we increase this, let's say to 30, and this, you see that these grow now again, so you need more inhibition again to counteract this. We go here to 33. Then this might be a good range. I tested this because before, this is why I kind of know. There's now a little artifact here because there was activation above threshold before. If something like this happens, like a stray peak, you can always go up here to this little button and reset the activation within the entire architecture. So if I click this, basically it resets everything to threshold, to resting level, and then sees again what is happening. This is quite useful if something is messed up. It doesn't change any of the parameters, it just changes the activation within the fields. So now if we take out an object here, and you fiddled with the parameters long enough, you'll see that I now took out the input. So this third object here in the top right corner, bottom right corner, but the peak stays, right? There's still a peak here. And even if I take out the entire scene, so I don't know, black out the camera in a way, by changing the strength of this static gain to 0, you'll see that all the peaks remain here. Right? If I put them back in, and also put this one back in, the peaks are still there, but they're again supported by input. So if I change one of the inputs, maybe change the position, you also see that the peak tracks that input. So it's not that the peaks, once they're in a self-sustained mode, they're completely cut off from the input, but they, they still couple to the input and they can track it. Good. So this is now a working memory field. This is the second section. And then there's the third section here, which if you go down a little bit, where you're supposed to do the same thing for a selective field. And we can do that real quick. So we close this, and then we create a new field. Again, we drag one down here, and we call this maybe selection. We add, again, the input to it by connecting these. And then we plot what is going on. And now, since this is the default parameter set, you'll see that it already created 3 peaks, and this is not what we want. In a selective field, we want only ever a single peak, even if there are multiple inputs like this. So 3 objects, just 1 peak. What we want, so the way we get there is by having global inhibition, a lot of global inhibition, so that if you have a peak somewhere, you want everything else pushed down. So this time we want global inhibition, but if we ramp it up to a high value, you'll see that it drags down the entire activation of the field, right? So we also, in this case, it's the other way around. We want a lot of inhibition, but we need the excitation to counteract that a little bit. So then we can increase the strength here of the excitation, and maybe a value that might work is something like 25 or so. And at some point you'll see that there's only a single peak, even though you have multiple inputs, right? And then a good test for this is that if you, let's see which object that is. The object that it has selected is the top left one, which is this one. So if we take this out, it should make a different selection decision to a different object, right? And here now you see that it didn't really work. So you tuned the field and it looked like it was making a selection, but it doesn't really seem to work over a lot of different input ranges, right? So now we have one object less, and it's not really selective much anymore. So maybe you need to tune this again and maybe change the inhibition more or make this a bit stronger. And at some point you'll find that, which one did I take away? This one. That it works over a broad range of stuff. That also, of course, means that you're not going to magically find a parameter setting that works for everything, right? It's always very much dependent on how large are these inputs, how many are there, and I think that's a realistic thing, right? You're not going to build the perfect machine there, but you're only you have this little piece of neural substrate which is optimized for specific inputs that it receives. Good. So this is a little architecture. It doesn't really do much. You only have these 3 different fields which are in different regimes, and what we really want to end up at is some architecture that has some kind of function. So this is something that you can explore on your own. Now that you sort of have a hint of how you get fields into the right regimes, there's an exercise here, the 4th task of the exercise sheet, where you build a small architecture from these elements that you already know. So it uses the same simulated scene input, and then you have a field which just is a representation of that. But then you have more function, and the idea is to build an architecture that from the scene selects an object based on where it is, so that you can say, I want to select an object on the left side of the table or on the right side of the table, or other regions that you may want to build. That's explained here. And this is something that you can do now with the knowledge that you have about CEDAR. And we'll talk about that tomorrow. I'll go through how that works, and I'll answer questions about that. In the meantime, again, use the discussion forum to ask questions about general stuff or about this, and we'll monitor this and go through that. CEDAR has a lot more different functions. For instance, you can also not just simulate stuff, you can also record data from it if you later want to publish it. You can add different sources. So I didn't do this here, but we could have also gotten input from a camera or from a video file or a picture. And we'll utilize some of these later for project work, so that you are not, you're not stuck to just using little blobs of input, but that you can use actual videos of objects moving around. And it also has connection to robotic software, and there's image processing and stuff in there. But it's quite a large thing, and a lot of stuff to play with.